My name is Catherine Yu. I'm a PhD student at the Sci-Fi Lab at Cornell University. Today, I'm very excited to present SeamPose, repurposing seams as capacitive sensors in a shirt for upper body pose tracking. In case it is not clear, the black shirt that Mary is wearing in this video, and also the shirt that I'm wearing now, is the shirt that we repurposed. This paper was done in collaboration with my amazing colleagues, Mary, Peter, Chiron, Cassidy, Saif, Redon, Francois, and my advisor, Chung. So I'm the last talk in this session named Poses as Input, and I thank the previous authors for motivating why this is an important problem to work on. So I hope at this point we all agree pose tracking is a fundamental task for healthcare, human activity recognition, AR/VR interactions, human-robot interactions, sports analytics, etc. So earlier we saw insoles and commercial devices solutions for pose tracking. Now I'm going to explain to you why clothing is a great solution for it. So first of all of us are wearing clothing right now, and clothing covers a large area of our bodies. Further, clothing naturally deforms, stretches, and shifts as the joints and muscles move. In fact, professional gray mocap systems require tight-fitting suits so that the reflective markers or miniaturized IMUs can be attached on them for high-fidelity pose tracking. Though I look quite happy over here, because it was my first time wearing a mocap suit, the suit was actually far from comfortable for everyday wear. On the other hand, loose-fitting clothing like the one that I'm wearing right now, or the ones that we wear on a daily basis, are comfortable for everyday wears. But that is also a challenge, as loose-fitting clothes has even more freedom to move around and does not perfectly conform to the body, posing additional challenges for building sensing systems. These recent works aim to tackle pose tracking with loose-fitting jackets. In mocap pose, Bo et al. Attached 16 patches of conductive fabrics as capacitive sensors on the jacket. However, as you can see in the images, the conductive fabric patches alter the clothing surface, affecting the look and the materiality. In LIP, Zhou et al. Attached 4 IMUs across the loose-fitting jacket and models the loose-fitting behaviors. However, while miniaturized, the attached IMUs are still rigid, and wire routings in the jacket needed to be carefully planned. To this end, we proposed SeamPose, an all-textile sensing system that provides fine-grained tracking abilities while minimizing surface modifications and maximizing the wearing experience. So what are seams? Seams are areas of overlapping fabric, usually inside the garments, formed by joining 2 or more pieces of fabric together with stitches. So if you flip out your sleeve cuff, you should see seams. So now we would like to ask all of you to take half a minute to look inside of your sleeves, tops, pants, and find the different seams on your clothing. I can see you if you're not looking. Okay, so you probably noticed that they're wide enough to fit some sensors, and they're conveniently distributed near our upper body joints. To repurpose the seams, we machine sew insulated conductive threads over existing seams, and we chose a common zigzag stitch for stretchability. Just like that, conventional seams are augmented into sensing seams with this silverish conductive threads. And because seams originally exist on the garment and remain concealed when worn, altering seams with conductive threads invisibly provide pose tracking capabilities. Note that we only repurpose or sew over existing seams and do not strategically add more seams to optimize for the best tracking performance. So seam placements are actually determined by the pattern, a set of templates. So these solid black diagrams are designed for cutting and sewing the fabric so that when you connect the fabric edges, they form garments. And the dashed lines here are where our sensors are placed on. So in the scalable cut and sew clothing manufacturing processes, fabrics are first cut into these shapes, and then they're stitched together. So our process has the potential to be integrated into existing manufacturing processes. And in SeamPose, for the proof of concept, we just picked a very common and basic long sleeve shirt, essentially an off-the-shelf pattern. And these SEAM electrodes are connected to a customized and tethered capacitive sensing board. If you're far away, you probably can't see it right now. So the board measures and transmits the measured capacitance of the conductive threads wirelessly via Bluetooth. So the colored lines on the leftmost illustration denotes the sensing SEAM placements. And these electrodes in this pattern are along the sleeves. They're colored in purple, in front of the sleeves covered in yellow, behind the shoulders colored in greens, and above the shoulders colored in blue. As you can see in this video, as Mary moves, the signals change correspondingly as results of coupling changes between the SEAM electrodes and the wearer's body, and also changes in SEAM electrodes' self-capacitance caused by thread deformation. So with these 8 channels of raw signals, we take 3-second window as inputs to a bidirectional LSTM backbone customized deep learning model and directly regress on joint rotations. To train and evaluate our models, we conducted a user study with 12 participants, covering a wide range of movements, including 54 movement sequences, 2 TikTok dances, and some freestyle movements. The evaluation metric we adopt is MPJPE, mean per joint position error, and because it is an error, the smaller the number, the better the performance. So we first train a user-independent model where we leave out the data for the tested participant, and then we fine-tune this model with about 23 minutes of data from the tested subject. So for our user-adaptive or user-dependent model, the MPJPE is 6 centimeters. We can capture pretty subtle movements, such as head movements. In these videos, this male model actually never collected any data before using the live inference system. In a user-independent manner, the model is trained with 8 hours of data from 12 participants and 7 researchers. For this leave one participant out evaluation, the error does increase to 8.6 centimeter, but still tracks the body really well in many contexts. For more detailed result breakdown, please see the paper. So now I'm going to do a live demo as well, and apparently we're all confessing whether we have backup slides or not. I do. But hopefully I don't use them. All right. As this is connecting, you'll see on your right there are 8 channels of signals, and you see that illustration again. So they're all correspondent colors, right? So when I move my right side, you see signals change on the right side, mostly. And then when I move my left side, you see signals mostly change on the left side. So I'm going to stop talking and just do a bunch of things. You can look at either the prediction or the signals. All right. Now I'm going to make my best attempt at doing a TikTok dance. I hope you remember the demo, but not the part of me dancing. Okay, let's go. Bear with me. All right. Okay. All right, no need for backup slides. Well, we don't need to see this. This concludes the talk. I have the shirt with me, so sorry. Anyway, I have the shirt with me. You're welcome to try out the shirt and play with our user-independent model. Some people already tried the shirt during our workshop demo session. And I do have a warning if you want to try it. This shirt has never been washed. You're wondering whether this shirt could be washed. We're working on it. Thank you. Now I can take questions.
Two questions here. Hi, I'm Shayna from Northeastern University. I was just wondering how your model accounted for things like seams bunching. I saw that it was like a long sleeve shirt and a lot of the gestures bunch up towards the elbow, and then things like diverse body types. So very often I've broken a seam on some clothing that is not adapted for curvy bodies in the bust or the hips. So being that the seam is often a high stress area, how do you account for those things?
When you say seam bunching, do you mean they get like scrunched up or like it's not perfectly conforming to my body?
Yes.
Okay, cool. So like I said, we had one prototype that has never been washed. So when we did chose a relatively large shirt so that we could fit all our participants. So right now I'm wearing a men's large, which I usually don't wear. So we did observe that the better fit the shirt is on the body, the seams will move along with your bodies better, and then it will like less likely to have the sleeve drops down when I move up, and also less likely to have seam bunching. So that does improve the performance. But we also realized that even with just 18 people's data for like 7-8 hours, our user-independent model was able to generalize across body types, across like different body shapes. So obviously, if you have a model with more concentrated data for a particular body types, or even make multiple shirts that are of different sizes, the predictions or the performance should be better.
Great, thank you so much. This was such a great piece.
Thank you.
Yeah, thanks, Catherine once again.